Good afternoon. I can hope you can hear me at the back. You can hear me? Good, excellent. Okay, so this is week 11, and the last topic that we will cover in this topic is design patterns. Okay, so have you heard of this term before? Anyone? What is this then? You're saying yes, I believe. Please go ahead to start the discussion. Yeah. Meanwhile, rest of students can also come to the class if they are late. Yeah. What is a design pattern?
From my understanding, I think it's like how you organize your thoughts.
How you organize your solution? Yes. So how we are, being a software engineer, we are providing a solution to a problem. So a solution, how well that solution is organized, okay, it is, we can consider it as a design pattern. Okay, anyone else? So organizing your solution. What is a design pattern? What do you understand? What does the term itself tell you? Design pattern. When we say there's some pattern involved, what does it mean? Repetition, pattern. And design, we're talking about solution. So repetition of solution. When it is repetition of solution, it means the problem is repeating itself. So there is a repeating problem, and for that repeating problem, we have a repeated solution. Why we are repeating that solution again and again? What does it tell you?
To solve the problem.
To solve the problem, but it solves the problem very well. When you see some problem for the first time, you try to attempt it and you solve it. But in that process, you learn something. I didn't do this correctly, I should have done this. When that problem appears against you, then you are in better position to solve it. But over a period of time, addressing that problem again and again, and you improved your solution, eventually you reach a stage where solution is now stable. Because the first time you applied a solution, there were certain loopholes. You addressed those loopholes in second iteration, in third iteration, fourth iteration. But after a few iterations, you realized, now this is a very perfect solution to this problem. When you gain this knowledge, you share this knowledge with the community. You write a paper, you write a blog post, or you maybe do a TikTok video maybe. Okay, so community knows about it. Then community starts using it. Then it becomes a standard in the community that if there is a problem and you are providing a solution, then this design pattern is the way to go forward. So this is about design pattern, and in today's lecture, slides are not displayed. Give me a second. Okay, and let me, why these are not displayed. Apologies, it may take some time. I need to figure out. Okay, there's a whiteboard. Overhead camera. No. Something's happening now. Yeah. Yep, I got it working. Okay, again, I don't realize which button I pressed, but eventually it's working. Okay, but next time I will be more careful and I will learn this pattern and I will be able to do it in a better way. Okay, so design patterns are well known in software community. When we design class diagrams, at class level diagrams, we have to apply these patterns so that when programmers start implementing, he don't make those mistakes that other developers had made when the class diagram that was given to them did not have those design patterns implemented. So at class diagram, when we are designing class diagram, detailed class diagram, we identify these patterns, okay? And I have mentioned in the assessment brief of your assessment that you have to identify at least one design pattern in your class diagram. Okay. Okay, before I introduce you to design patterns and a couple of things about software architecture, I believe you must have received an email regarding student evaluation of teaching, SET, okay? And because you are knocking your head, it means you already know about it, the importance of this, okay? In this, it's very important you basically appreciate what worked, but also point out what didn't work, okay? And in that, if you have some suggestions, okay, again, that will give us good insights how we can better address them, okay? As I mentioned in the start of this lecture, in this one topic, I have to cover many aspects of software engineering so that when you go to the industry, you should at least be aware of these and at some hands-on skill as well, okay? So I tried, I revised the entire contents, and in doing that, I structured them in certain fashion, I delivered them in certain fashion, assessments in certain fashion. So if you felt difficulty or if you felt something could have been done in a different way, please do give us a feedback so that when I deliver this topic next time, I can incorporate that feedback. And if you like few things, give us feedback as well, because if one student say, this should be done in this fashion, so on, and there's no other voice in the feedback that would have said, okay, this is good, I learned it a lot. So we need a balanced voice, we need both viewpoints from the students, okay? And unless we have a comprehensive feedback from the students, it is difficult sometimes for the instructor to basically update the contents. Relying on one student, what he said, if I update the contents, maybe other students may get adversely affected by that. Okay, so I will appreciate all of you if you spare some time and provide your feedback. Okay, higher the response rate would be, it will be good for me to basically assess the quality of the topic. Okay, there's one video which they have informed us to show you, but I believe you already know about all that information. Okay, so before going to design pattern, I will just give you an idea of what is concrete architecture. Okay, in your assessment, you have reflected upon it, and which is good, but still I thought because this is a last topic before going to design patterns, I should just give you an idea. And then we will basically go through design patterns and the classification of design patterns, why we classify them and what are the classes that are important for us to understand. So if you recall, this was the case study that we discussed in one of the previous lecture, Track Manager, where we have these clients, and these clients basically need to interact with Tracking Manager. Okay, this query client needs make synchronous request. It means when it send a request, it waits for the response. Whereas update client just do the UDP packet sending, just send the package and don't expect response. And this is the persistent storage where they basically Track Manager basically store and retrieve information. So this is conceptual architecture that we define initially. If you recall Twin Peak model, what was Twin Peak model? If someone can recall, Twin Peak model. As soon as you start capturing the requirement, start working on design as well. Okay. In agile software engineering, we start capturing the requirement. In parallel, once we have enough requirement, we start working on design as well. And architecture is one of the important deliverable in design. And Twin Peak model basically emphasizes this. So initially, in start of our software development life cycle, we basically start with conceptual software architecture. And after that, we basically define these quality attribute scenarios. Okay? And these scenarios are for entire system, because the architectural quality are the features are emergent behavior of a system. Okay, so these are pertinent to entire system. How well perform? What is the performance you're expecting in the system? What should be the fault tolerance, and so on. So in that regard, we basically discuss these three quality attribute scenario. So if something wrong happened, the system should recover quickly. There should be a mirror replica of that service that should basically take on when the primary instance basically breaks down. We have slow recovery. Okay, if we don't have infrastructure, we don't have resources, at least we should save the state of the system so that if the current instance crashes down, we can start running another instance and we can load the state from the persistent storage. Okay, that was slow recovery. Third was, okay, some disaster has happened, so now we have to restart the system. We need that functionality as well. So in doing so, the architect basically drill down further and they come up with the concrete architecture. So concrete architecture is the one that basically address the quality attribute scenarios. The things that are identified in quality attribute scenarios, they are reflected in concrete architecture. So we are moving from conceptual to concrete. Now, whatever we have identified in quality attribute scenarios, that should be reflected in this. Okay, so you can see that initially we had very simple, only four components. 1, 2, 3, 4 components in there. But because of identifying these quality attribute scenarios, now our architecture has changed. We have many more components. Okay, we have this, for example, instead of having one instance, we have two instances of track manager, A and B. So that if A is busy, B can receive the request. If B is busy, A can receive the request. Okay, so this again adds certain increase in performance, because we cannot hold on these requests in a queue for a long period of time. But if this track manager fails, we have another instance. Okay, and that instance may be mirror, or if it is not a mirror, then we have the information about the state of the track manager saved in secondary storage. So if this crashes, primary system crashes, that is running both A and B instances, then the secondary systems can start running. If it is not replica, then it can read all the status information and can load it and start serving those clients. And on top of that, we have this fault tolerance service, because in real environment, now the request from these clients need to be forwarded to this another machine. So we need a proxy server, and that proxy server holds information about this, the primary as well as secondary. And this health monitor service basically looks at the health of the replicas. Okay, and then accordingly update the proxy server so that the request can be directed to the track manager that is currently running. Okay, and we have some other services as well. Registration service, naming services. These are basically whenever a new client comes into the system, it needs to be registered. Naming service, basically requests go to naming service in order to identify what are the IP address at what port request needs to be made. So those are implementation related constraints. But in short, what we need to understand is, initially the conceptual architecture was important domain level concepts, that the knowledge we acquired from the client, that client, the context in which we are working, we have clients, there are two types of clients, and they are interacting with the client manager. That's it. But when we have identified quality attribute scenarios, the non-functional requirements, then we identified that fault tolerance and performance, for example, are the key attributes. And we need to update software architecture so that these attributes can be addressed. So in that regard, we update the current architecture with certain additional components to achieve those quality attributes. So this is concrete architecture. So in this topic, my expectation is not that you basically understand all these concepts with thorough detail, quality attributes realization. But the important thing that we need to understand is that domain level concepts that we identify and are part of software architecture, after defining these quality attributes, that architecture gets revised, and that architecture after revision is the one that should be implemented eventually. Okay, so this is how conceptual architecture and concrete architecture changes. In your assessment, many students basically, I'm not sure whether they looked at the instructions or not, but they basically, instead of going client server or layer architecture, they went for microservices architecture. Now microservice architecture is good. It gives you flexibility, it gives you more reliability, and fault tolerance is very high. But that is not for monolithic application. Monolithic application is that your software is not divided into small components, not small services. Rather, it's a one system. Okay, so the case study that we are using is a monolithic system. Okay, and the class diagram that you have identified, it is for one system that may consist of subsystem, but overall it's a monolithic system. Okay, unless your system consists of very small components, then microservice architecture is more suitable. But anyway, I'm not going in more discussion of that. But conceptual architecture revises after quality attributes, and concrete architecture basically reflects the real implementation of architecture. Questions? Anything? Then we can go to design patterns. Anything regarding architecture, software architecture? Good? Clear? Okay, so design pattern. Before going to design pattern, I just want to assess your knowledge of Java. I believe all of you are doing Java programming. Okay. So have you covered interfaces in Java? Good. So you know about polymorphism? I'm not asking what is polymorphism, just I want you to know that you have covered it. Okay. You have covered inheritance, composition, everything. Okay, so then it will be good, easy for me to go through. But I will be happy to answer your questions if you have any ambiguity. Okay, so design patterns. As I started my discussion earlier, design patterns, as the name suggests, there are certain recurring problems, and for those problems we have recurring solution. Okay, and solution is used over a period of time, and now it's become a standard. We call it design pattern. In order to understand design pattern, I will take you through this small study, which is again I took from this book, which is a link I have provided to you. That basically highlights the importance of design pattern. A problem will become apparent as we basically start working on the design class diagram, and then we realize that inheritance and compositions are two features of a language. Okay, and it's up to us to identify where those features should be used, where we should use inheritance and where we should use composition. So these are features of language. Language comes with all possible features. Okay, it's our job, being a designer, to identify, to understand each concept, and in current context, whether we should go for inheritance or composition, and what is the importance of interfaces as compared to inheritance when you design a solution. Okay. So in order to understand this, let's assume that you worked on a application which is Simulation Duck, and this is a simple simulation app in which you basically have developed an app that simulates different ducks, okay, swimming in a pond and so on, and kids basically love that application, and you release that application, your company release that application, and everything is going fine. Okay. So before I go to this, so for designing this application, which is Simulation Duck, what do you think? Which is the most important entity or the class we should start with? In duck simulation, the duck itself. Okay, so we should have a duck class. Okay, and we know that there will be many ducks in the simulation. We have one duck class, and we can create multiple objects of the duck class. But those ducks would have different features. Duck A would be different from duck B will be different from duck C will be different from duck D. So how we can design for this? We have a duck class, but for creating all those ducks, how we should proceed? What language feature we should employ so that we can create ducks of different types. Yes, we can go for inheritance. Okay, we can go for inheritance. We can define a superclass duck, and we can define specialized classes. Like parents, they have children. Each child is different. Okay, but they inherit the properties of their parents. So what we did, we basically created a duck class, and from duck class we inherited different child classes. Now, duck class is an abstract class. So what is an abstract class, first of all? Do you have to be loud? It hides all the details of implementation. Very close. Someone wants to add to it? It hides all the details of implementation. Is this correct? Pardon? Not instantiated. Yes, that's correct. Abstract class are not instantiated. They are just for structure, the skeleton. And that structure we achieved over here. But they don't hide away all the details. That's the difference between interface and abstract class. Okay, what's the difference between interface and abstract class? Abstract class, we know it can't be instantiated. This is for the structure, and that's the strength of object-oriented programming. Okay. So difference between interface and abstract class. That will answer this question, the point which your fellow student basically shared. So abstract class and interfaces, they are two different things. But how they are different from each other? In abstract class, you can define some details. You can define some details in abstract class, but interface, no details at all. There are two things in Java when we talk about methods. One is definition, second is declaration or implementation. Definition and implementation. Can someone tell me how they differ? What is declaration and what is implementation?
Like predefined values is the declaration.
Okay, and what is implementation? Implementation is method. And what is signature of method? What is a declaration of method? So there are two things. In abstract class, we define a method, but we don't give the implementation. Implementation might be in specialized class. Okay, so that's why in Java we say it's a declaration and it's implementation. Declaration is, for example, variable int x is just a declaration. Okay, unless you assign a variable or assign a value and so on. So that's just a declaration. In method, when you just define a method in interface, that's declaration. But when you implement that interface in Java class and provide the functionality, that becomes implementation. Okay, before going to the topic, we can address these concepts. Okay, so we have abstract classes, we have interfaces. Okay, what is the purpose of defining interfaces? Why we define interfaces? Abstract class, we got an idea. Okay, there's some common behavior that we can capture in abstract class, and child classes can inherit those features. Why we define interfaces? Take your time, no worries. We have 2 hours. Flexibility. But how to define this flexibility? What sort of flexibility we are talking about over here? Object?
Content of the methods.
Implementation of the methods. We decouple, our interfaces helps to decouple implementation from usage. Okay, interfaces help us to decouple the implementation from where they are being used. And what is the advantage of this decoupling? When we decouple, and I will show you an example, okay? When we decouple, a usage of that interface, again that interface is being implemented by some object, some class, and we create an object of that class, but implementation of that interface would be maybe another class. So this decouple helps us to easily update the software, easily maintain the software. When we have this decouple between usage and implementation, we can easily maintain the software. We discussed about architecture pattern and style. That object-oriented style, the key strength of this style is reusability and easy maintenance of the code. Okay, so when we decouple implementation from the usage, then we can update the implementation as many times as possible. It will not affect where it is being used. Okay, you can update the software, you can update the methods, all the implementations that you have done for that interfaces. It will not affect it. Okay, so these are some important concepts, and in this again design patterns, they are important to understand them. And you will see that all the design patterns, they are in object-oriented programming. Okay, object-oriented style is used to depict these design patterns. Okay, coming back to the problem. So we have this duck simulation class, and what we have over here. So quack and swim, these are common behaviors. This mallard duck and red-head duck, both of them swim, both of them quack. Okay, so that behavior we defined over here. So we have definition as well as implementation in that abstract class. Object-oriented programming, the objective of object-oriented programming is we should write minimum code to achieve functionality. Now we might have 80 classes over here, 90, 100, but for all of them, quack behavior and swim behavior is defined over here. And if we want to update the software, we want to update the quack behavior or swim behavior, we just need to make change over here. And all the classes that basically extend this duck class, they will get updated. So that's the strength of inheritance, object-oriented programming. So these behavior could be quite complex, but we don't need to implement those behaviors in each and every class. So if we create a new class that extends duck class, this behavior will be inherited. So that's the strength of inheritance. But display is something which every duck would have unique appearance. So we cannot give implementation of display over here. So we can declare display over here, and implementation would be in each child class. Okay, so we were able to achieve advantage of inheritance over here, but in case of display, we need to override their display method. Okay, so you know about overriding in Java. Okay, so we have a method display over here, but in this, that display method is overridden by the display which is being coded in each class. So we can have display, unique display for each duck. So far so good. Okay. After a certain period of time, new requirements basically comes in. And we discussed in the first lecture that in software engineering context, you have a customer, you yourself software engineer, system you need to build, and the fourth important component was environment, in which basically software works. Okay, university using LMS, and university has an environment, and if something changes in environment, LMS needs to update it. So that environment again brings in the challenges for software engineer to accommodate these new changes. Okay, so a change come in that okay, your simulation app is excellent, we can see the ducks, they swim, they quack, and each of them are different, appearance is different, but now we want them to fly as well. This is a requirement. So what do we do now? How we can incorporate this change? We have this design class diagram over here. Okay, we didn't mention attribute over here, but we have methods over here. Okay, so what we should do now? We have to incorporate this new feature, which is ducks should fly. So how I can accommodate that change. What should I do now in this design class diagram? Loud. Add fly method in duck class. Make sense? Okay, that's good enough. Okay, let's take advantage of inheritance again. So we can add fly method in the duck class. And by doing just this add in one class, entire software gets updated. We don't need to do anything in all the child classes. Okay, good enough. But change coming again. Now the new change is we need rubber ducks now in our simulation app. And the rubber duck don't quack. Rubber duck don't fly. So we have fly method over there. We have a quack method over there. But the new change is we need a rubber duck. Now, the previously which was thing was very powerful, like inheritance, just add in parent class. But now this new change is quite challenging. We need a rubber duck, and rubber duck does not quack. Okay, it may squeak, sound would be different, but it does not fly, definitely. And we have a fly feature over here. What we can do then? So rubber duck has some different features than those we have captured as common behavior. So this abstract class, what it captures? The common behavior, the common attributes. Okay, but now rubber duck comes into the play. The sound of rubber duck would not be quack. It would be different, and it would not fly as well. Okay, so what we can do now? Just remove those methods, and then do what? What about fly? We want ducks to fly. This is a solution. Remove those methods. Remove those methods from parent class and put them in child classes. Okay, this is one solution. Remove the methods quack and fly from the duck class, and now you can put those methods in each class. It means you have to update all the classes. You need to, if you have 100 classes, you have to update 100 classes. Where is inheritance now? It's gone. Okay, so that is one possible solution. What other solution is available? Override. We can override. This is only one class. You know, when you're working a team, we say for time being, this is only one scenario. Let's do it. You sometimes hard code something in your code just to make it run in your final year project. Instead of having something dynamic, you just hard code some information to make it work. So override we can do, because in override we don't need to worry about the rest of the classes, but the new class that we are going to include, we just need to override these methods in that class. Okay, so for example, this duck does not quack, or it's a squeak. Okay, a different sound. So we can override that method. Okay, similarly, it does not fly, so we can override the rubber duck with fly method. So only this is the class in which we are doing overriding. So we are not getting the advantage of inheritance, rather we are writing extra code to override the common behavior, because this class does not have those behaviors. Okay, so initially we were using advantage of inheritance, but now we are overriding the current functionality. So this was rubber duck, and we did it quickly because this is only one class that we need to override the functionality. We overridden this functionality and we release the software, and everyone is happy. Okay, so for time being, our solution worked. But what if a new duck comes in? Decoy duck, which don't quack, which don't fly. So what we should do now? The changes that are coming in now, they basically are challenging the design that we initially proposed. That design is not working for these new changes, isn't it? We instead of having inheritance, we are overriding. We are writing more code now, isn't it? I think the problem is quite apparent over here. That inheritance is not paying well for these features. It means there are certain features that are common. And we can see that every duck swim. Okay? Swim is still there. But other features, they are showing us some diversity. There is a variation involved from one duck to another duck. And those variations are of a great deal. Okay? And if we continue with inheritance and new requirements keep coming in, then we would be overriding existing functionality. So it means inheritance is not working well for us. So what we should do now? What do you think? We didn't go through these slides before because I uploaded these slides last week. Solution is there. So think of it that there are certain features that are basically that vary from one duck to another duck, and inheritance is not giving us a solution for those features. The way initially we thought that abstract class will give us the solution and we just need to extend the rest of the classes, that is not working for us. What we should do then? So we, at least the first solution which you mentioned previously, we need to remove those things from the duck class. Inheritance is not working, and putting these features in abstract class is not working. So if you have designed a class diagram, okay, in your design class diagram, you have a duck class and you came up with a solution that that every duck will swim, every duck will display, every duck will do this and this, and if there is any duck, one or two, we can override the methods, then it's not going to work. Because requirements will keep coming in. Okay? And by doing this, you understood that there are certain features that are common, but there are certain features that vary to a great deal. So this is the problem. Okay, how to address this problem leads to identification of design pattern. Okay. So how we can address this? First of all, we remove those features that are not common. Okay. So in abstract class, those features that are not common, we remove them, and instead of having an abstract class, we created interfaces. We created two interfaces because we know that fly and quack behavior. These are the two behaviors that are changing from one duck to another duck. Each duck has its own fly method and quack method. Okay. So we pulled out those features from these classes, and rather than putting them over here in this, we basically identify the interfaces. This is the first step we did. This is not the ultimate solution. This is the first step that we identified that, okay, common behavior should be in abstract class, but those features that are showing variation, we can capture them using interfaces. Now, these ducks can implement those interfaces and can give you the functionality. Okay? But the challenge is, fly behavior can be of different type. Some may fly going straight and then coming down like a triangle. Some may go zigzag. It's quite possible in simulation. But at the first state, we identified that we have to pull out those features and identify these quack behavior interface. So this is the first step. So we can define these interfaces, and these interfaces can be then implemented. How they will be implemented, we come to the final solution. Okay, but these interfaces can be implemented by a class that needs that specific behavior, and they can code that behavior. Okay. So how we can achieve multiple inheritance in Java? What is multiple inheritance? Multiple inheritance. Inheriting from more than one thing. but you can extend only one class. But you can implement multiple interfaces. So multiple interfaces, through multiple interface implementation, you can achieve multiple inheritance in Java. Okay, so if there's a class that needs to implement both behavior, they can implement both interfaces. Okay, so decoy duck can implement fly interface and can code the behavior over there. But again, over here, initially our solution may work, but it's quite possible that the fly behavior is also changing, and every time new behaviors comes in, we need to update the usage, how that is being used in the code. Let me show you next slide. Yep, this is about polymorphism. So instead of abstract class, we use interfaces. Okay, and we know that we can achieve polymorphism whether we have interfaces or we have abstract class, isn't it? What is polymorphism? Did we discuss it at the start? No. What is polymorphism? Have you heard of this term before, polymorphism? Okay, that's good. I have an example on the screen. Inherit the behavior of different multiple classes. Okay. We have to be careful when we use words, when we know about those things. When you're a new student, you can interchangeably use different words for different things. Okay. So what is polymorphism? You're right. Your intent is right. I'm just looking for the correct words. Yes? Different children can be assigned to a variable of parent class. Okay? So those words are more near to what he was explaining. Okay? So we have example over here. This is programming to implementation. And you have done programming. So if you create a new object of a certain class, basically you assign it to variable of that class. So dog is a new class, okay, and you basically create a new variable D of type D dog. Okay, so this is programming to implementation. This is programming to interface, okay, or super type. That could be an abstract class. So animal is a super class, abstract class or interface, and these are two child classes. So we want to maintain the software. Okay, we want to make minimum changes to our code which we have done. And one way is a good practice is use programming to an interface of super type. So in this case, we have defined a variable of animal data type with animal, and we can assign any animal that is derived from this animal class. And rest of the code, we don't need to make any change. So this aspect that you have programmed according to the interface will help you to maintain your code for a longer period of time. You just need to make change over here. Which type of animal that you want to create. Rest of the code, you don't need to change. So this is programming to interface or super type, whereas this is programming to implementation. So we want to achieve polymorphism, okay, in this case study as well. And this is the final solution. Okay, let me take you through, and then we can take a break. So you can see that this is a duck class, and in final solution we are going for composition rather than inheritance. Okay, you will see that we have a composition over here. First of all, give me. Okay, so first of all, this is This is the first interface, which is fly. Now fly can have different implementations, okay? And we have two implementations over here, which is fly with wings and fly without wings, for example. We can have multiple implementations over here. We can have as many implementations as possible. But all of them would have implemented this interface. Okay, I will repeat. Because of this interface can be implemented in as many behavior of flying as much possible that you can define over here. So we think of each set of behavior as a family of algorithms. Okay, so you can define different types of behaviors, as many as possible, as long as they implement this interface. Your code on this side don't need to change anything. Okay, no matter you choose this algorithm, or any other algorithm, as long as that new functionality, new fly behavior implements this interface, there would be no change on the code that you have implemented in this duck class. Similarly, we have quack behavior, and quack behavior can have different implementations. Some are quack, some are squeak, some are blah blah blah, and so on. So you can have as many as possible. As long as they are implementing this interface, there would be minimum or even no change on the code on this side. Okay, why? Because in duck class we have composition. And what is composition? Composition is basically whole part relationship. So this duck class is composed of fly behavior and duck behavior. So recall the composition and aggregation. Okay, so this is composition. Duck class is basically consists of quack behavior and fly behavior. That's why we have these two variables, reference variables, created over here, and we have given them certain names. So these are placeholders for fly behavior and quack behavior. Those behavior will be assigned to duck class, but how, we will see. But in the skeleton of duck class we have these variables, and this is composition. This duck class does not extend something, does not implement something. Rather, you just create an object of fly with wings, fly without wings in this class, and assign to these parent class variables that achieve polymorphism. Okay, because of polymorphism we have these two variables, and we can assign any object that we create from any of these concrete implementation classes to these variables. Because of polymorphism, now our code is more maintainable. Okay, and we have different methods over here, and these classes basically extend from duck class. So over here we have used composition. So in short, if there are certain features in your parent class that are showing certain diversity among the specialized classes, so it's better to pull out those behaviors, implement them using interfaces. Okay, each behavior should be implemented through interfaces, and consider them as series of algorithm implementing that specific behavior. Okay, so this is a solution to this problem. So again, I will summarize. Problem is certain behaviors are changing, and inheritance is not paying off. We go for composition, and we achieve composition through polymorphism interfaces. So these are the two interfaces, these are two placeholders, and these are specialized classes. If I show you this, can you see this code? Okay, let me zoom in. So you see this is a Mallorer duck, this one, and you cannot see the cursor on this. Okay, so we have a Mallorer class that extends duck class, and within the constructor of duck class. So what is the constructor? Create an instance. Whenever you create, when you write new keyword, this method is called, which is called constructor. So whenever new method is called, whatever you have done in this method, that code will run, and it will initialize basically object with those values. So in the constructor of Mallorer duck, we have quack behavior is equal to new quack, new squeak, new ABC, whatever behavior you want. Okay, so this is composition. Fly behavior, new, fly with wings, fly without wings, fly horizontally, fly vertically, whatever fly. Okay, so those behaviors you can assign at this point of time. And rest of the code that you have coded in duck class are specialized duck classes. They are using these quack behavior and fly behavior variables. Okay, and that code will still work. Okay, because these are variables of parent class. So the object, new quack object will cast automatically and will be assigned to this quack behavior, which is the reference variable we defined in this duck class. Okay. So this is the code over here. You see, this is duck class, and duck class we have fly behavior.fly. We have this statement in the duck class abstract class, but this fly behavior is the reference variable, and whatever variable whatever object we have assigned at the time of creating the object, that behavior would be called when we call this fly method. Okay. Similarly for quack method. So these methods are in abstract class, but the behavior will come from the composition that we have achieved. And this is the code where we basically have interface. Okay, interface is defined, and that interface is being implemented. Okay, so these two classes implements their fly behavior, and you can code what type of behavior you expect from that class. So this is how we can code it. Okay, and when we can create a Miller object class, object of this class, constructor will be called new quack behavior and fly behavior that we define in the constructor, that will be assigned to this Miller duck, and duck is again abstract class. Polymorphism we are achieving over here, and this is a variable of that abstract class. So rest of the code, Miller dot perform or whatever variable you define over here, that code will work, and you don't need to change anything. It all depends upon what kind of object you want to create. Okay. Again, this is example of that Miller duck that we have discussed. So this is the first pattern that we have covered, which is called strategy design pattern. So there was a problem, and we addressed that problem and provided a solution. And community, software engineering community, basically applied this pattern again and again, and then they gave it a name which is called strategy design pattern. So whenever there are certain behavior of a entity that vary to a great deal, entity has some common behavior, and specialized classes can inherit those behaviors. But there are certain behaviors that are different from each and every object of that class. So in order to address that, you can apply this strategy design pattern. So you have a context. In this case, it was duck context. So we use composition. We define a fly behavior interface. So this strategy, one strategy is basically representing fly behavior. Similarly, we have another strategy which is quack behavior. We can have another strategy and so on. So there could be multiple strategies. So strategy is the behavior, one behavior that is basically varying. In order to achieve that behavior, this is an interface. This interface defines that behavior. We can have different implementation strategy. Fly with wings, fly without wings, fly on wheels, fly blah blah, and so on. Okay. So through this interface and composition and these concrete implementation, we achieve strategy design pattern. Questions? Everything is good? Okay, so then we can take 10 to 15, 15 minutes break. Okay, so we'll be back at 2:10. Okay. Meanwhile, if you want to show me something, any of your work, or any other questions, I will be happy to answer them. Let me pause the recording. So, strategy design pattern is the first pattern that we covered in the first half of this lecture. So design pattern, as we discussed, they are recurring solution to recurring problem. But one important thing we need to understand is they are not prescriptive solution. It's not like that they will give you exact coding level solution to your problem. Rather, this is a design template. They will identify the core components, and then you have to basically understand and implement in your system. Okay, so these are not prescriptive solutions. Rather, these are a little bit high-level design templates that can guide you to a better solution. And it has, and especially in the definition, look over here, that the core of solution to the problem in such a way that you can use this solution 1,000,000 times over without ever doing it the same way twice. So people are implementing it, but none of those implementations would be exactly the same in terms of code. But at design level, they are the same. So there are various design patterns that have been documented. There's a very famous book, Gang of Four Design Patterns, in which various design patterns have been documented. If you Google on internet, you will find many design patterns. We can group the design patterns into 3 categories. Structural design patterns, all those design patterns that relate to assembling the objects, the classes, they are basically put in this category. If design patterns concerned with interaction of the objects and classes, we call them, put them in behavioral category. If the design pattern concerns with creation of the objects, how objects should be created, then we put them in creation design pattern. So we'll go through a few examples from each of these categories. Beside with each design pattern, it comes with a motivation. What is the problem? Like in strategy design pattern, we identified the problem, and intent is what is the solution. Each design pattern comes with the overall structure and what are the components which are called participants in that solution. So each design patterns will come with these 4 pieces of information: the problem, the solution, the important components, and how those components are structured. What is the interaction among them? So adopter design pattern is a structural design pattern because related to the structure of object. So in order to understand this design pattern, let's look at this real world example. We know this problem very well. If our plug does not match the socket, what we do? We use the adapter. Otherwise, there are other solutions as well. If we don't use the adapter, what other solutions do we have? Come on, guys. If we don't use the adapter, what solution do we have? Cut the wire and attach another plug or change the socket. But you can change the socket in your home, but if you are in a hotel, then you cannot change the socket. So there are situations where we don't want to change existing classes, existing infrastructure, and we bring in a new component that can help us to overcome that heterogeneity, that inconsistency and so on. So this is adapter design pattern where basically, again, I'm not going into intent and motivation in detail, but I will try to explain in simple terms that what this design pattern wants to achieve. So we have certain classes, okay, for example, representing this wire, and we have certain other classes that we want to reuse, for example, but they don't match with each other. So we can bring in adapter. For example, if you look over here, this is a client, and client want to use, so this client is a wire and this adaptee is the socket, okay? So this client want to use the functionality of this adaptee. This adaptee basically can serve some specific request. This is a method signature over here. But the interface that is available is basically have this signature of method request. So this interface is being implemented by the adapter, okay? So this interface is implemented by adapter, and within that implementation of adapter, this method request, within the implementation of this method, the specific request of adaptee is being called. So in short, this client has a reference variable of target data type, okay, so this interface, and this adapter implements this interface, and within the method of request, it creates an object of adaptee and calls a specific method of that adaptee. You got it? Let me show. So this is a design pattern. This is a high level implementation, and this is one of the realization in code of that design pattern, where we have a client, we have a target functionality, and we have a adapter that basically helps to achieve it. So this is the client, okay? Client wants to use to retrieve banking details of a certain person, for example. And this banking details is a class that does not belong to this package. It is from some company, and we cannot change this. We cannot change our class, and we cannot change the target as well. So this is the wire, and this is a socket. So we don't want to change the wire, we don't want to change the socket. So what we did, this is an interface. Okay, this interface is being implemented by the adopter, which is bank customer. Bank customer basically implements the methods that are defined in the constructor. Within these methods, it is calling the methods of bank class. Okay, so adopter help us to achieve that functionality. If I show you the code, so this is first of all the interface, credit card. Okay, it basically provides the definition of two methods. And this is the bank details. So this class is not in our control. We cannot change it. This is the banking class, okay? And this is the adopter class where we basically, if you look over here, we basically extends the bank details and implements the credit card. So we are extending this bank details class because we have access to it, and we are implementing the interface, which is client basically have a reference object will be created according to this reference placeholder in the context. Okay. And then we have the context where we are using is the client. Okay. If you look over here, within the client, we create credit card. Now this credit card is a super type reference object, okay, variable. Okay. And we are creating new bank customer. This bank customer object will be casted to, casting will be done to credit card, and then credit card method will be called. And this is the method that is being called over here. In this method, we are calling the method of account, customer account, get account name and get bank detail. Because this bank customer is extending bank details class, so it means when we implemented this class, all the methods of this bank details, they are inherited in this class. So because of this inheritance, we are able to call these methods get account number and get account name, and then we return these methods, and these will get printed when we call this method over here. So this is adopter design pattern. Okay. In the workshop for undergraduate, I have given a link to a resource where all these design patterns are implemented. And this week and next week, what you need to do is you need to go through few design patterns, copy paste that code, implement them, and then try to understand them, how they have been implemented, and look at this design diagrams that I am sharing with you. So this is first design pattern, which is adopter design pattern. Another example of adopter design pattern is, let me show. Okay. So what we have over here, so this is the editor, this is the context, okay? And this editor wants to use some functionality of text view, which is again socket example, if you recall. Okay, we just want to reuse this functionality, but we cannot make change over here, and we cannot do any change over here. So what we do over here? So this is an interface, and this interface basically declare two methods: bounding box and create manipulator. And we have two classes, concrete classes, that basically implement that interface, line shade and text shade. Okay, and within these concrete classes, bounding box method, which is from this interface, is being implemented. But within these method, get extent, which is the method of this object, is being called. Okay, so within bounding box, we are creating an object of text view and calling get extent method, and the result would be returned to editor. But over here, instead of only giving adopter facility, we have additional functionality as well. Create manipulator. So in this editor, there's a canvas, and we not only want to create object, but also want functionality to interact with those objects, to manipulate those objects, move them around, for example. So then within this adopter, we added some additional functionality. Create manipulator, and we basically create some new functionality and return that manipulator to this class. So this text manipulator is not being implemented in this class. So this is additional functionality. So what we can make from this? Adopter help us to bridge the communication gap gap, okay? But in doing that, we can add additional behavior in Doppler as well. We can add additional functionality in Doppler as well to basically extend that functionality of that application. So this is a Doppler design pattern. Second design pattern is facade design pattern. If you look over here, we have a system which is some kind of CD player or sound system. We have different classes. We have amplifier, tuner, DVD player, projector, CD player, blah, blah, and so on. If you want to create new sound system, what you need to do? You need to create, first of all, your own class, for example. Okay? And then you need to create object of amplifier, you need to create object of CD player, you need to create of popcorn popper, and you need to create object of as many classes as possible so that you can achieve the functionality of complete home theater, for example. This is home theater application. So you are building home theater application, and this is already some package available, some source code available, open source, for example, and you want to reuse it. But in case you want to reuse it, you need to first of all go and look at the details. What are the important classes? What are the interactions? And in order to develop a complete home sound system, whatever, you need to create multiple objects, and you need to also identify interactions among those objects. So you need to look into the details of those that library, for example. Okay, so there is a lot of burden on you. And secondly, if the author of that code, the producer of that code, updates certain classes, it means all the code that you have written needs to be updated as well, isn't it? For example, if previously it was there was interaction between tuner and amplifier, and the producer changed these interactions some other way, then definitely the logic you have over here needs to be updated. So the reusability of the code is quite challenging over here. Okay, so this is a problem. If first of all you need to go through a lot of details to implement the solution. Secondly, if there is a change in the code, existing code, then definitely it would have impact on the code which you have written. So high coupling definitely leads to a lot of challenges. We need to reduce the coupling. Okay, we need to increase the cohesion and reduce the coupling. In this scenario, cohesion is low, coupling is high, and we are trying to reuse this code. So facade design pattern provides a solution. So instead of exposing your software and letting it leaving it to the client to basically understand and compose the application, you should basically have a well-defined structure like facade design pattern over here that will basically hide away all the details from the client, and client just need to interact with this one class and achieve this entire functionality. So facade design pattern hides away all the details, and user just need to understand this one class and build a complete home theater system. So this is facade design pattern. And this is the solution where now, instead of previously this code was exported, now they have a parent class, facade design pattern being implemented over here, where this class basically implement all the possible methods to realize home theater. And how the system work is hidden from the client. Whatever changes the producer wants to do, they can do any change over here. As long as these methods remain same, this class remains same, the client code don't need to be updated. So this pattern we see when we work on frameworks, APIs. Okay, they are developed using this facade design pattern. They hide away all the details, and you just need to call a couple of methods to achieve the functionality. Okay, so this is the second design pattern, facade design pattern. Third design pattern is composite design pattern, and we know that in, for example, a paint-like application, we may need to create and draw many objects on the canvas. Okay, and if you see over here, we have different types of objects. We have circle, we have line, we have rectangle. Okay, we have to create all these objects and then we have to write statements for each of these objects to draw them on the canvas. What if you have 500 objects, 5,000 objects? Would it be feasible to write 5,000 draw statements over there? Absolutely not. So what could be the possible solution? If we have 500 objects and we have to call the method draw 500 times, what should we do? Group by how? And you are doing Java, so give me the data structure. Loop, okay, loop. Yes, we can use loop, we can have a list, or we can have an array, and we can loop through it. Okay, but with array, there's one challenge. Array can hold object of only one data type. List can hold multiple objects, but again, when you need to draw call method, then definitely you need to have either polymorphism or something like that. Okay, so polymorphism provides us a solution over here. So what we can do, we can define an interface. Okay, so we can define an interface, user interface. So this is an interface, and this, all the shapes that we have in our canvas, in our system, they can implement that interface. Once they implement that interface, then definitely we can use data structures, loop lists, array list or arrays or list for looping through to achieve that functionality. So we have interface, and each object triangle, they implement that interface. Then what we need to basically put them in an array list so that we can loop through, and we can add all the objects into the array list, and then we can do the casting. So this is polymorphism over here. So no matter which object it is, as soon as we want to loop through, it would be picked from the object array list, and it will be casted to this object, which is IOBG, and of this data type. And we need just only one statement over here to call the draw method. So again, polymorphism, we can see advantage over here. So this is a composite design pattern. Another example of composite design pattern is basically, we know about tree structures. Okay, so when we have tree structures, they go like this. Okay, so if a node has a child, we call it as a composite. So this is a composite node, this is a composite node, and these two are leaf node. Okay, so what we have over here, so client is the one that is going to use this. This component is an interface, and this interface is implemented by this composite object as well as leaf object. And if this composite object have childs, then we can add those childs to this component. So it is a recursive call over here. Okay, so through this, again, composite design pattern, we can capture tree-like structure as well, where we have this interface implemented by this composite class, and composite class basically implements the method that are declared in an interface. So if it is a composite object, it will add the new component which is being created into itself as a child. And if new child has a component, then it will create a new component and add it to itself. So it's a recursive call over here. Again, this is a composite style structure. So those are structural design patterns. Okay, important thing is understanding. Okay, you may not be able to implement all of these, but understanding is very important, that anything related with the structure, one package you want to use with another package, there's interfaces does not match, you want to basically the number of objects is quite high, you can use polymorphism. So all these are basically structural design patterns. So behavioral design pattern, we already covered. Strategy design pattern. Another is iterative design pattern. So this is behavioral, this is interaction of the objects. We know that in big teams, different developers basically work. And while each developer is coding, they might use different data structures. For example, we just discussed list and arrays. Okay, list and arrays, they differ from each other. List can have objects of different data types, but array can have object of only one data type. Arrays are fixed, whereas list can be dynamic. So if you are going to reuse that software, and you are going to retrieve or assign values to those data structures, then you need to know whether the developer has implemented a list or an array. For example, there are different methods that you need to call depending upon data structure. For example, for a list you need to call this method size, then you can get the size. But for array you need to call length method. Okay, so if you are exposed to these details, then definitely you need to understand first what type of data structure has been implemented, then you can interact with that data structure. So how we can address this? If you're doing Java, you know about iterators. Okay, so when we basically have a certain data structure, along with that data structure, iterator for that data structure is also available. So these iterators basically they implement an interface, no matter it's list, array list or arrays. They implement an interface. In that interface, these methods are declared. First, next, is done, and current item, and index, for example. Okay, and if when we implement this list iterator for the list, then we can define the functionality over here. And now if someone wants to use our code, then simply what he needs to do is, he needs to use our object, name of our object, and just call the method get iterator. This will return the iterator, and that iterator is implementing these methods. What is first, what is next, what is the current index, and so on. Now this developer don't need to understand low level details. He can just access the iterator and can get the size, or if size is there. Otherwise he can basically move to the first element and second element and so on. So this is iterator design pattern. Another is observer design pattern. In certain, look at this example. So this is a weather station app, and this app basically displays temperature, humidity, and pressure. This app is getting data from this weather data object, and this weather data object pulls information from weather station, and weather station, has these sensors attached to it. So weather stations are continuously pushing information to weather station, and weather data object is pulling information and display. Now it is useless if this weather data object keep on pulling data all the time and display it. Okay, logically it should only pull the data when there is change in the temperature, humidity, or pressure. If there is a change, this will pull the data and update the information. Okay, so this is quite a common problem where basically we want to receive only information when there is a change. You will only receive a mail, surface mail, when there is a mail for you. Otherwise you will not receive it. Okay, so this is another view to look at same problem. So these are the different views, and they are depicting different information. So they are observers, they are capturing the information, and this is a subject that is receiving the information. If the state of any of the observer changes, the subject basically need to notify rest of the observers to update their state. Okay, so these three observers, they are depicting same information but different views. So it's the same information that is depicted as Excel sheet over here, as a graph over here, and as a pie chart over here. It's the same information. Okay, so if one observer observes a change, then we need to notify other views as well so that they can get updated. So for this we use observer design pattern, and this is the structure of observer design pattern. So what do we have over here? We have two interfaces over here, subject and observer. There are multiple observers, so they need to register with the subject. So this is the concrete implementation of subject, and this is concrete implementation of observer. So first of all observers need to be registered with subject. Okay, so that's why we have attached and detached method in the abstract class, or you can say interface of the this subject. And in concrete class we either have their implementation, or we might have their implementation in the abstract class. Okay, so but what do we have over here? So these observers are registered, and as soon as the state of observer changes, so this state subject state is the observer's subject state is a variable that will get changed if there is certain change in the data. Okay, so if there is a change in state, then notify method is called, and this notify method basically iterate through all the observers and call their update method. Okay, so whenever update method of observer will be called, what is coded in that observer? It has access to the subject object of a subject, and it will call the method get state of the subject, and this method of subject basically return the current state, and observer will update himself with that current state. Okay, so this is how this observer pattern work. I can understand it may be overwhelming for you to you will not be able to grasp each and everything right now, but important thing is to understand that design patterns are well defined solution for specific problem. Okay, the problem over here is there are multiple observers observing the information, and they are reporting to the subject. As soon as one of the observer basically detect a change and update and send the data to subject will change its state and will update all the observers. Okay, if this is a scenario, then this design pattern will work. So those are behavioral design patterns. The last one are creational design patterns. So these are all about creating objects. Okay, if you look over here, we have a pizza class, and order pizza is a method. So this is a pizza class. Okay, order pizza is a method, and order pizza needs a string, and depending upon what type of pizza customer want, these if else structure basically create a pizza type and do rest of the things on the pizza and return the pizza. So this is simple pizza class. If the client says that okay, we need to add more pizza variety in the app, what we need to do? We just need to add if else structure over here. If it comes with another change that I need this pizza as well, then you can add another if else structure over here, and you can keep on adding as much as a client wants. But the important questions come when you incorporate a change in the software. You need to test the software, you need to compile and test the software, you need to write test cases for the software. Okay, so if you keep all these things in one method where you are creating an object and as well as processing that object, then it means when you go for testing, you need to test this entire class. Okay, although there is a section where you made a change, only this structure, but you need to compile entire class that can have this functionality as well. So testing becomes cumbersome. So what we can do is we can remove this behavior, the behavior that keeps on growing, okay, into a separate class, and we call this class simple pizza factory, because we are creating a pizza. So we create a new class which is simple pizza factory class, and we create a method create pizza, and it will take in string, and according to string it will create a pizza and will return to order method. So this is what we have done. Now regarding testing, we just need to test this class. Whatever functionality over here, we don't need to test it because we didn't change that code. We will only test that code where we have made a change. Okay, now we have pulled out that behavior and we put it in a separate class. Now we can compile it, we can test it, we can write test cases as well. So eventually our class would look like this. So this is pizza store. Okay, and pizza store we have this method which is called order pizza. Okay, in order pizza previously we had if and else structure. Rather than if and else structure, we have a method now factory dot create pizza. This one line. Now this factory is an object of simple factory class that we define on top of within this class. Okay, simple factory, simple pizza factory, and the object name is factory, and we pass this as a constructor to this pizza store. Whenever pizza store object is created, a factory is assigned to it. Okay, and the factory which we have created is simple pizza factory. Okay, so this This will initialize the pizza store with certain pizza creation method with simple factory. Now we can have multiple factories. We can have factory for some other pizza type. We can have factory for some other food items. The only change we need to do is create those behaviors, create those classes. But at the end, we just need to pass that factory to this class, and rest of the code will start working. So all those factories, if they implement the same interface, for example, then we achieve polymorphism as well. Okay, so this is abstract factory pattern where all the creation of the objects we pull out and we create a separate class that creates those objects. And we name it like a factory. Factory basically create objects. And then when we want to create a pizza, we assign a factory that can be used to create those pizzas. Okay, so this is abstract factory design pattern. There's another singleton design pattern, for example. You know, and on the websites, we want to know the number of visitors. So every time visitor comes, we don't want to create a new object. Rather, we want to just increment the current object. Okay, to have one instance of one object of a class and don't create no more object, we can use singleton design pattern. So no matter how many customers will visit our store, the same object, the counter, will be used to increment each time. We should not create a new counter object. Okay, so for those kind of things we use singleton design pattern. So you will see if you Google on the internet, there are various design patterns available. Now one distinction that we need to draw is how design patterns are different from architectural pattern. Okay, so architectural patterns are very high level of abstraction. We are talking about software architecture. Okay, so they are coarse, they are system level. Where design patterns are very much detailed, not in terms of code prescriptive, but they are much detailed as compared to architecture pattern, and they are local. You see, we are creating an object through abstract factory. We have iterator design patterns, we have composite design pattern, we have strategy design pattern. So they are very local. So design patterns are code level solution. So design class diagram, at that level we apply this design pattern, where architecture pattern are much higher level and they apply to entire system. And this picture depicted very well that if you know design pattern, it's a good knowledge. But don't start applying your design pattern to your solution. Because you know 12 design patterns, you start applying them to your solution. No. The need for design pattern will arise naturally. As you will design, you will see this problem is appearing, and then accordingly you can use that design pattern. Okay, so don't go other way around where you know the design patterns and you start implementing. Rather, start working on your domain problem, keep building your design class diagram, and then through deliberation try to identify what are the problems over there that you can face. What are the behaviors that are common? You can use inheritance. What are the behaviors that are not common? You can use strategy design pattern and so on. So need of the patterns will arise naturally. That's it for today. Questions? So next week we will have a guest lecture. Okay, and after guest lecture we will have some time and we will just I will be very happy to answer your question. I will quickly revise the contents and what I missed that I wanted to cover and what I covered so far, so we can have that discussion. But this basically ends your topic over here. Okay, but in this week workshop and next week workshop you can work on design patterns. The more you will code, some of these examples which I have given you a link in the for your workshop, the better you will understand. If you are able to implement only a couple of design patterns, you will understand the concept very well. Okay, and in your assignment you have to identify at least one design pattern, and this is for undergraduates only, one design pattern being reflected in your design class diagram. Okay, that's it for today. If no questions, then I will see you next week. Next week we have guest lecture. I will encourage you to come so that you can have face-to-face interaction with the speaker. Okay, and I will definitely share the details of the speaker and the talk in few days. Okay, before the lecture. Okay. Thank you very much. Have a good week. See you next week then.